Yeah, I already abused some of my freedom here to add an extra word to my title and to write this on the board I'm not supposed to write on. And so now, and I should also give credit to Eric, because his idea that I should add another double to the title. And so let me then try to cook up some reason why I added a double. So essentially, what I'm going to talk about today is mathematical aspects of gauge theory and gravity, very basic stuff. And there's two aspects to it. So one of them is the double copy, so let me write it here. But there's a related concept, which I will come to briefly, which we call color kinematics duality. And so the double copy refers to some property of gravity. And if I'm, sometimes it's hard to explain what it is, but if I try to explain it to a first grader, I would say that, well, it's just a statement that 1 times 1 equals to 2. And then the first grader would say, nah, that's wrong. You meant plus. Well, what I really mean is I mean that if you look at spin 1, and you tensor it, spin 1, and you tensor it with spin 1, then you get, of course, spin 2, according to quantum mechanics. Maybe I'm now a bit above the first grade's knowledge. And that's kind of a trivial statement, but nonetheless, it's a true statement for states that we scatter in amplitudes, for example, so asymptotic states. So states. And you can try to take this idea one step further, and you can try to look at the interactions. And remarkably, it seems to work. So if I look at, say, let me just talk about an amplitude, 3-point amplitude, which basically describes the 3-point interaction. So if I take 3 gluon amplitude and multiply it with another 3 gluon amplitude, and now it's a true multiplication rather than some tensor product, remarkably, you get a gravitational amplitude for 3 gravitons. And I'm going to use A for gauge theory amplitude and M for gravitational amplitudes to make it clear. So this is interactions. And then you can take it one step further, and you can say, well, I mean, this is just the simplest interaction. Maybe it's just an accident. So you can say, what if you go further, like more non-trivial processes, amplitudes, whatever, and you can say, well, maybe I should just think that there is some relation between the theories. So maybe I should just think that maybe there is some kind of operation between two copies of Yang-Mills and GR. That's not quite true. There's some other stuff that you might also get, so let me just put a dot here. But basically, this is some relation at the level of theories. And you can also ask, there's other things besides amplitudes in gauge theory and gravity. For example, there are solutions to the equation of motion. And it turns out that there's also similar relations there. So for example, people have figured out that if you do the Coulomb solution and you do an appropriate operation, which is also some bilinear, then in fact you get a solution in GR. You get, well, maybe not the simplest one, but one of the simpler ones, which is the Schwarzschild solution. And that's slightly different than how you do it for amplitudes, so I will come back to that later, maybe this afternoon. But that's basically the very concise summary of what the double copy is, and of course I will go into details.
This is great. Totally
Sorry, ahistorical. Yes, I will come back to string theory later, if you just forgive me. Well, I think the tensor product of states has been known for a long time, but I will come back to string theory. All right, so yeah, so what's the joy of this? So the joy here is that we have some new mathematical properties in gravity, and by new, I don't mean new compared to 2 or 3 decades ago. I mean new compared to the original formulation of GR, right? Basically, we're no longer seeing, the geometric description that everybody enjoys in standard GR, but we're seeing something new. We're seeing some factorization, and there's something behind this. Another joy of the double copy is that it actually simplifies your calculations in GR. So if you want to compute some high multiplicity process in GR, as far as we know, this is the best method to use. Let me say, so that was 2 positive aspects. One slightly negative aspect, or depending how you see it, could also be positive, is that we don't actually understand why GR or why gravity behaves like this. You could go back to string theory, but I think there's also mysteries for string amplitudes which are not understood. So there's some mystery here, even to the people who have studied this for many years. There's also mysteries that we don't understand. All right, so then let me come to color kinematics duality. So this is a property of gauge theories, but it's intimately related to the double copy. And I would say, well, if you ask me, I would say that you can, double copy is actually a derived property from color kinematics duality. So if you assume color kinematics duality, then double copy is almost trivial. So the idea here is that, we're gonna generalize. We're no longer necessarily gonna look at Yang-Mills. We're just gonna pick some gauge theory, and we're going to say there's going to be some operation like this, where we get some gravity theory. But this operation only works if the gauge theory satisfies some special properties. So the property that they have to satisfy is there has to be a duality between color factors and kinematic factors in this theory, so in the interactions, in amplitudes, and so on. And of course, the color factors come from our gauge theory. We can pick it to be SUNC. Just pick some large NC. That doesn't really matter exactly what it is, but we don't want to use any. We don't want to use any finite n properties. So don't pick 2 or a small number. And then there has to be some corresponding kinematic property that behaves like your gauge group. And to be fair, we don't actually know exactly what it is, but typically we refer to it as just some kinematic Lie algebra. And I will come back to it later. We don't know what it is, except in some simple cases where we know it, but in general we don't. Yeah, sure.
So the SUNC, are you relying on large NC?
No, I'm yeah. Yeah, good question. Yeah. I don't want to be specific, so I just want to use generic Lie algebra properties, so Jacobi relations and commutation relation. Any finite n or any large n, or, yeah, I don't want to use that. Because essentially what you want to do is that you want to make this, whatever this is, the kinematic Lie algebra, it has to behave the same way as this. So, if you take some large n here, you have to take a large n here, whatever that means. And I don't think you can do that, so you basically have to just say something which has is something which has the algebraic properties, and you need to make that on both sides. Okay, and you might wonder, well, what does it actually mean? Well, it means that we're going to describe our amplitudes as some kind of Feynman diagram. Some Feynman diagram that we're going to write as having some color factor and some kinematic factor. And then we're going to separate out the propagator, so we're going to treat them differently. So that's going to be some propagator factor in the denominator. And this one is going to just be not play a role in this color kinematics duality. It's only going to be the kinematic numerator and the color factor, and they're going to be dual to each other in some sense.
So is the background shifting Minkowski on both sides of this?
Yeah, so since I'm looking at amplitudes, I want to at least have asymptotically Minkowski. But of course, in the gauge theory, yeah, it's just Minkowski. Some people have, well, I'm not sure. People have looked at ADS and de Sitter correlation functions, and things seems to also work in that case, but there's some complications, so I'm not going to really talk about it. But here I'm just going to assume flat space in the gauge theory and asymptotically flat in the gravity theory. Okay, so just as in the double copy, the joy is that we have some new mathematical structure here, this kinematic Lie algebra, whatever it is, in well-known theories such as Yang-Mills, but also in other theories. And another joy is that it often makes calculations simpler. So some of the state-of-the-art calculation has actually been done using this, I should say, in supersymmetric theories, but we can go to quite high loop order. And one slightly negative thing, or positive, depending how you see it, is that we don't understand it. We don't understand the kinematic Lie algebra, whatever it is. Does it exist? We don't know. So that's mysteries. And mysteries can also be good, of course, because you can write a lot of papers. So a lot of papers have been written on this topic because there's still a lot of confusions. Okay, so I should say I put some references here. So these are 3 reviews. This is a very long review. This is some shorter reviews. I should also mention that I'm not going to talk about phenomenology because there is not so much connection to phenomenology yet. I tried to find 2 papers which at least made an attempt. So there's a paper here by Campbell and Keith Ellis, which was doing some top quark amplitudes, 3 level, but you know, I imagine they're going to use it for some phenomenology. And then I put the paper here by, well, the only person I know is Mikado, and they're using it in some context of EFTs. I think if you look at these papers and look at whoever cites them, you might find other paper which do similar things. Okay. Maybe one thing I will mention later on is I will mention an axion, not the QCD axion, but there's an axion that plays a role here. And the reason I mention that is because 2 weeks ago we had a talk by Anson, and he also mentioned that there is a connection between axion and double copy. So I will talk about it slightly. Also, I should say that Shruti will give a talk in a week, I think, where she will actually say some more about related to double copy, and I guess we have to cook up some exactly what's going to be said there, I guess. Yeah. Okay, so let me erase. By the way, is there any more questions? So let me start by saying it's quite surprising that there is a relation between Yang-Mills and GR because the theories are quite different, right? So if I just do a naive comparison between Yang-Mills and GR, with the Lagrangian is quadratic in the curvature field strength. Here, the Lagrangian is linear in the curvature. You can do a bit better, of course, if you look at the equation of motion. I have to remind myself what it is. Okay. So in the equation of motion without any sources, at least now they're linear in the curvature and the gauge theory curvature. But it's still very different, very different. But because they're both linear here, if I go to weak coupling and I look at the very simplest solution I can imagine, which are plane waves, the plane waves are actually very similar. So if I go to weak coupling, plane waves, then, of course, the solution is just that the gauge field is some color factor, some polarization times e to the I p dot x. And for gravity, also going to weak coupling, so I'm just going to assume I basically have a free theory. The metric has two factors of, well, it really has a polarization tensor, but I can always factorize it, especially in 4 dimension. It's very easy to factorize it. And e to the I p dot x. So here you see that, well, they're very similar, in fact. And the only difference between them is that the gravity polarization has 2 copies of a polarization vector, and it's actually the same polarization in the 2 cases. It's basically something which is transverse. That you can also take them to be null, such that it's traceless. And also, you can shift your polarization by something proportional to momentum, which is basically the gauge invariance later on. But basically, there's an operation that takes me from the gauge theory solution to the gravity solution, and that's basically replacing the color factor, which is some vector in color space, and I replace it by a vector in spacetime, which is the polarization. And that's the operation that takes me from there to there. Alternatively, you can just say that I'm throwing away the color and I'm doubling the polarization, so that's why it's called double copy. Sometimes people call it a square, but it's more appropriate said a double copy. If you notice, one thing that I don't do is that I don't do anything to the plane wave factor. I don't square it. I just leave it alone. And that's actually very important. That's a general feature. When we talk about amplitudes, I'm going to leave some factors alone, which are the propagators. And of course, the plane wave factor and the propagator are intimately related. After lunch, I will probably talk a little bit about the classical double copy. There's also going to be a scalar function that you're going to leave alone. So that's the general feature. And later on, when you talk about amplitudes, of course, you can remove the plane wave factors by just integrating over x. That gives a delta function. You should not square delta functions because that gives very bad amplitudes, bad distributional factors. Okay, good. So now, after having talked about the trivial case of plane waves, let me now talk about scattering plane waves, which is basically the amplitudes. Yeah. I'm allowed to have 2 different, yeah. So let me actually put some helicities. So we know, of course, that in 4 dimension you have 2 helicities for the gluon or the photon, and for gravity, naively, then you get 4. But what we do in order to get pure gravity is that we always correlate. So you put either 2 plus helicities or 2 minus helicities. You could pick different plus minus, which is essentially what Schroeter is referring to, which would give you like an asymmetric double copy of the polarizations. And that would give then other states. It would give something which has no helicity, so that's either a scalar or a pseudoscalar. And in general dimension, it would just be an antisymmetric tensor. But to get pure gravity, this is what you do. You make sure that you correlate the helicities. You can also do this in higher dimension to get just the graviton.
Does that make this look more straightforward if you write things in the language of brains, like that?
Brains?
No, frames.
Frames. Does it get better? Well, I mean, of course, you can hope that maybe this is just obvious. You know, if I factorize my metric into frames, you know, maybe it all comes from there. But you know, people have looked at it and it doesn't seem related to this, I guess. Yeah. So the fact that you can factorize your metric has nothing to do with the fact that you can factorize your amplitudes. They seem completely independent.
So at this point, if you have this operation,
yeah.
Think about the inverse.
Yeah, so the inverse.
There's only take you to the scalar sigma.
Oh, you mean if I replace epsilon by another color factor? Yeah. So that's also something you can do, of course. Then you just get the scalar theory, which has two color factors, and people typically call this bi-adjoint phi cubed, because what you get is basically just trivial cubic diagrams. That was known for a long time. I mean, basically since we started working on this, it was known that you could always do that. But from some point of view, you know, that seems like a trivial theory. Like, you know, who cares about phi cubed with 2 color factors? But then in the last 10 years or so, people actually noticed that it's quite interesting theory, has a lot of properties. There's also a lot of recent work by Akani Hamed and company where they don't look at the bi-adjoint theory. They look at just trace phi cubed, but they're related in the sense that, you know, there's a subsector of bi-adjoint scalar theory, which is just trace phi cubed. Okay, good. I mean, you can also, another inverse, I mean, this is what I was thought you asked originally, is that, you know, how do you go from here to there? Well, you can just do some compactification, I guess, some Kaluza-Klein compactification. So in some sense, what we're doing here is that we're doing the inverse of that. Okay, good. So let me now start talking about amplitudes. So let me first now define in words a little bit more what the double copy is. So the double copy in a narrow sense, this is a narrow sense, it's essentially just the statement that you can obtain GR amplitudes well, GR amplitudes are bilinears of the Engels amplitudes. And maybe I should say that, well, you have to be a bit careful here. So what I mean here is that at tree level, they're bilinears. And when you go to loop level, there's a map, but you have to do it before you integrate. So the integration makes it a bit more complicated. But that's essentially the narrow sense of what the double copy is. And I chose to say that we're doing this order by order in the gauge coupling. So we do tree level, map between tree level amplitudes here and tree level amplitudes here. And then when you go to one loop, you do one loop here, one loop there, and so on. So in some sense, there's some kind of weak relation between gauge theory and gravity. And yeah. I should also say that eventually I'm going to even more refine the amplitude, so it's going to be a map between individual diagrams, but I will come to that. Okay, and then a remark, and this is related to David's comment in the beginning, is that this statement, of course, has been known for, what is it, 40 years now, maybe? Yeah. And this is known at tree level from string theory. So in string theory is known as the quasi-level and tie relation. Or sometimes open-closed relations. Close. And it's basically, let me write it out how it looks like. So you have your closed string. And it's just given by some sum over some permutation. Let me not specify. It's basically permuting the external legs, but not quite all of them. And then you have open string, which is defined for some ordering, which has to do with the sham pattern factors, sigma, and then you have some kernel, which people call KLT kernel, which is typically written like this. It's basically a matrix. And then you have another copy of OpenString. So roughly that's how it's been known for a long time. And this S here is just some polynomial in the Mandelstems inserted in, well, it's really a polynomial of sines and cosines where you have arguments being Mandelstems. Well, this permutation is basically over the permutation group of n minus 3 particles. Okay, and of course, once you have this in string theory, you can always take the string alpha prime to 0, so infinite string tension, and then you get field theory relations. Naively, you get supersymmetric amplitudes, but you can always do a projection, so you get bosonic, and you also get just pure GR and pure Yang-Mills. Yeah? Tree level.
So I have a question about that. Just quite practice my ignorance about what's the state of the art. So yeah. On the amplitude side, the multiplication table for double copy is now quite rich. I'm sure you're going to talk about it. It's more than just Yang-Mills squared.
Yeah.
Equals gravity. So I have things involving multiplying things like pieces of various nonlinear models like Born-Infeld and so on and so forth, and getting this very rich structure, which is all accounted for with color kinematics duality. But are there avatars of that in string theory as well, that richer multiplication table for all the examples?
Yeah, very good question, yeah. Well, first of all, here, since you have a supersymmetric theory, you can start doing truncations of the fermions and scalars and so on, right? In lower dimensions, right? So if you can always truncate to various degrees, and you can even do truncations differently on the two sides here. And that already gives you a huge multiplication table. You can do n equals 4, you can do n equals 2, n equals 1, n equals 0. So that's a big table. I guess you're more thinking of the nonlinear sigma model. Yeah.
How do those come to the string picture? Do I have to have some?
Yeah, I think you can also do some operations to get that, because OpenString, of course, has some interactions which corresponds to the nonlinear sigma model. You just have to expand to the next order in alpha prime, and then you have to abelianize it. That might cause some trouble, because here I have orderings, but I think that's the simplest way to see that you could also maybe get the nonlinear sigma model, but you might have to work a bit harder.
The question is, has it been done?
I don't think it has been done, actually, yeah. So somebody in the audience should work on it. Yeah. I think it comes back to this question, can you derive everything from string theory, or is there something new here? And I would like to say there's actually a lot of new things. One example which I often bring up, which maybe is not so well known, is that you can get a theory that's called, so there's n equals 2 supergravities of various kinds, and some of them are called the magical supergravities. And they actually, there's 4 of them. There's a real, there's a complex, there's a quaternionic, and an octonionic. So it turns out that the real, complex, and quaternionic one, you can derive from string theory, no problem. But the octonionic one, nobody knows how to derive it yet. Yeah. Yes. Oh, that I don't know, but at least it makes sense at the low energy level, I guess. Yeah. So as a supergravity, it makes sense, but I don't know if, I mean, you can ask if it makes sense when you UV complete it. I don't know. I think if you ask the experts, so the expert is Murat Günaydın, he says that he thinks he knows how to derive it, but he has not yet written the paper, so there's some complications. Maybe I shouldn't say that. But anyhow, so currently it's not known how to do it, but it's actually known how to get it from a double copy. So the double copy is actually quite straightforward. Okay.
Sorry,
yeah.
So, of course, you talked about amplitudes. You'll tell us about classical solutions after lunch. Is
Yeah.
there any sense in which, instantons or Diploid manifolds have?
That's a good question. I'm not the expert. There are some people who has worked on non-perturbative solutions. There's Chris White at Queen Mary. He has looked at a lot of solutions. I don't know actually what exactly is the status there. I don't know if somebody in the audience knows better. I think there's a lot of things to be done there. So let me not comment whether it works or not, because I don't know. Yeah. Okay, good. Okay. Yeah. Oh, yeah. So another comment related to this is that, of course, we got this remarkable relation from string theory, and we also got a lot of information from string theory, in the 70s, 80s, and 90s. People computed QCD amplitudes from string theory. But I would say that in the last 20 years, people are actually using field theory properties to compute string theory amplitudes. And in particular, they're using the double copy. They're using the field theory double copy to do computations in string theory, which is quite interesting. So for example, there's like a state-of-the-art calculation, which is 3-loop closed string, or genus 3 closed string by Iwan Geyer, Ricardo Monteiro, and another Ricardo. And they're actually using input from gauge theory, from n equals 4 super Yang-Mills, well, dimensionally uplifted, of course, to n equals 1 in 10D. And they're using that input to actually compute the it's a candidate for the 3-loop amplitude, which needs further verification, but it is state-of-the-art. I guess I should have put the reference there, but yeah. Anyhow, so that's my point, that we're actually learning things about string theory by using this. So in that sense, it's new, I guess. Okay, good. So now let me write down some explicit expressions. All right, so I want to write down some 3-point amplitudes, and then after that, we're just going to write some schematic equations. But let's play explicit. So let's start with Yang-Mills. I'm going to use calligraphic A for the full amplitude, and now I'm just going to say it depends on 3 labels. So we have our G Yang-Mills, well, with G coupling, I guess we have a color factor which is just the structure constant. We have some kinematic factor, which is just eta mu nu, P1 minus P2 rho plus cyclic in the labels 1, 2, 3, and also cyclic in the mu nu rho, I guess. Let me just write it like that. And then we have some polarization factor. Okay, so that's our 3-point amplitude written just according to what the Feynman rules gives you. Now you can try to do the same thing for gravity. So Einstein gravity, you have some coupling as well. Typically we write it as kappa over 2. Kappa is related to g Newton, basically square root of g Newton times some numerical factors. And then there's the kinematic dependence, which looks actually the same as upstairs. But you square it. Let me also put the polarizations in there. Oops, wrong way. Squared. So that is your gravity amplitude. So you see that all I did is I took this factor here, squared it, but I did not include the color factor, I did not include the coupling. And if you actually do, I mean, so here you of course recognize that this is just whatever you get from the Feynman rules, but this is not what you get from the Feynman rules. So if you actually use the Feynman rules for gravity, which was first written down by Bryce DeWitt in the 60s, I think, you actually get something, I think it's actually 170 terms. You can maybe try to improve on that, using some field redefinitions and whatever. But before you impose on-shell conditions, you get something of the order of 100 terms. But as soon as you use the on-shell conditions, so on-shell conditions are basically just that, the momentum squared is 0, polarization dot momentum is 0, and also you have to use that the polarizations themselves are null vectors. So if you impose these 3 conditions and momentum conservation, then this 170-term expression collapses to this. It's pretty cool exercise, actually. You should do it. It's nice to see when something messy collapses to a square. Same thing happens if you do 4-point calculation in GR. Use the Feynman rules. It's an absolutely horrendous calculation. You impose this condition, it just becomes a square times some trivial STU factors. Okay, good. Yep. Yeah, so the reason why they have to be null in this case is because we want the graviton to be traceless. And we write it as a product of 2 epsilons. And you might worry, well, am I not over-constraining my polarizations? Well, in 4D, you can convince yourself that if you just go to what's called circular polarizations, of course they are null vectors, right? So in 4D, there's no constraint. But even in general dimension, you can always decompose your polarization tensors into complex polarization tensors, which are null. And you can always write something real in terms of something complex. I mean, this, just add and subtract the complex conjugate, right? You might also worry, what about massive W bosons, right? Because we know massive W bosons have 3 states. So if I try to generalize that to that case, how is it going to work out? Well, it turns out that even in that case, you can do it because you can associate your complex polarizations with W and the other one with W bars. You can make sense of it. It works. Okay, good. Now, usually when people give these talks, they don't show you the Feynman rules. They usually show some simpler spin helicity expressions. So let me also show you that. So if I actually use some fancy technology where I replace my polarization vectors with bilinears in on-shell spinners. Then things collapses to something much simpler. So let me do that. So now I also have to pick my helicities. Okay, so let me, for the gluon, let me just pick minus, minus, plus. And in that case, you can write the amplitude in terms of some bilinears of spinners. I'm not going to explain what they are, but these are just some valve spinners and in a product of two valve spinners. So that's how the Young-Mills amplitude looks like. And now I have dropped the coupling and the color factor because I don't want to write them all the time. And then I just write a straight A. And then for gravity, also let me drop the coupling and just write a straight A or straight M. So if I pick the same helicity, you have to remember that for gravity, this is of course twice the helicity of that, but I'm going to write it the same way. And it's just a square. Well, just a square. Okay. You might wonder about other states. So now I'm just looking at the graviton and the gluons. You can say, what about if I had some fermions, scalars, or whatever? So you can convince yourself at 3 point things are just trivial, because I can write, in fact, the most general amplitude for 3 massless particle. So if I have helicity 1, helicity 2, helicity 3, there's a very simple formula for this amplitude. So it's basically just a product of this inner product spinners, and you have to just write some powers here. So this is H3 minus H1 minus H2, 2, 3, H1 minus H2 minus H3, 3, 1, H2 minus H1 minus H3. That's the general formula for any helicity. And you can convince yourself now that if the helicity is 1 or 2, they're going to be related by a square, just because this is a power. This is a simple monomial. I can always factorize this monomial in 2 factors. Those factors are going to be gauge-theory amplitudes. So it's always going to work. Okay, good. So that covers 3 points. And so I guess I should go on to 4 points then, unless there's any questions about 3 points. Oh. Actually, let me just I'm going to erase it shortly, but let me call this 3-point vertex just V mu nu rho. Just to find my vertex of Young-Mills. So then I'm going to use it for my 4-point calculation. Okay, good. So let's do 4-point. Let me now simplify the notation a little bit. Let me just write this A4. And I'm just going to write some diagrams. So these are diagrams for Young-Mills. We're going to have an S-channel graph. We're going to have a T-channel graph. And we're going to have a U-channel graph. Now, you could have more, which is, of course, a contact vertex. But what I'm going to do is I'm going to ignore this. And I'm just going to absorb it into the other diagrams. Because I can always, even though it's missing a propagator, I can always restore a propagator and put an inverse propagator in the numerator. And then this becomes a function that has the following form. So that's an S-channel diagram. It has some color factor. I'm just going to call it CS. and it has some kinematic numerator, which I'm going to call n. Then likewise in the T channel, and likewise in the U channel. Okay? And I don't think I have to define what ST and U is. I hope people know what they are. But let me define, let me first define what CS, the color factor in the S channel. So it's just a product of two Fs, two structure constants. So it's FA1, A2, then some intermediate particle or color index A3, A4. So this is my color factor in the S channel, and the other ones are just related by permutation, so I don't even need to write down. What is my numerator in the S channel? Well, let me just take this vertex that I had on the previous slide, the 3-point vertex. Let me contract it. Let me just write it as 1, 2, nu. He has one Lorentz index, and then he has two saturated polarizations. And then we have d nu 3, 4. So this is just my Feynman rule. But since I moved this diagram into the rest, I have to write something more. I cannot just use the Feynman rule, so I have to write something which is proportional to S, because S and S upstairs has to cancel S downstairs in order to give me a contact term. And then you can pretty much figure out what it is by symmetries. So it's epsilon 1 dot epsilon 3, epsilon 2 dot epsilon 4. And then the diagram has to be antisymmetric in 1 and 2, so I have to subtract where 1 and 2 is flipped. It's pretty much obvious, the only thing you can write. I cannot write epsilon 1 dot epsilon 2 because that would never be antisymmetric. I want something antisymmetric. It needs to be antisymmetric because this is antisymmetric, so I cannot multiply something antisymmetric with something symmetric. Okay, good. So this is the only thing you need to do. You need to tweak your Feynman rule slightly by adding this term, and then you can convince yourself that when you then sum over these three diagrams, you just recover the usual Yang-Mills 4-point vertex. Okay, good. Now, a crucial aspect at 4 points that you're not going to encounter at 3 point is that your color factor, CS, CT, and CU are not independent. They're dependent. And the relation, of course, is that you have the Lie algebra, so the SUNC Lie algebra, which gives you the Jacobi identity, which is just, in this notation, it's just going to be CS plus CT plus CU equal to 0. If I just define them to be permutations of, let's say, 1, 2, and 3. If I permute those three, then the sum has to be 0. Okay, good. Then color kinematic duality just says that our numerators, which is given by this expression, plus the permutations, has to satisfy the same expression, the same relation. And indeed, the one I wrote here actually does that. You can check yourself that the sum of NS, NT plus NU is equal to 0. Somehow it just works accidentally at 4 point. I mean, I didn't do very much. All I did is just absorb the 4-point vertex, and it worked. Yep.
If you had absorbed it differently, would that work?
Well, so here the only freedom I have, like if I want to make sure that I have like a permutation symmetry between the graphs and antisymmetry of the graphs, then the only freedom I have is basically the overall factor here. But in order, if I want to get some gauge invariant, I don't even have the freedom of the overall factor, right? So just getting some gauge invariant actually uniquely fixes it. Sorry, what was the question again? Yeah, you could also relax some of the permutation symmetry and then make your life a bit more complicated. But often things just work automatically at 4 point. It's a bit of an accident. Yeah.
So my limited understanding of this is that rather than putting in the Jacobi identity from the algebra, it comes out just asking for locality, factorization,
Yes.
on poles, etc.
Mm-hmm.
So is that a general principle that I expect? I could cast the ends in the same light, and then presumably that should also follow to arbitrary order. Is that established?
In fact, that's what's the next thing I'm going to talk about. I was going to talk about just the 4-point case. I guess you were asking a more general question at endpoints. I think the answer is yes at 4 points. I think at higher points it's a little bit more complicated whether everything follows just from consistency. But let me do the 4-point case, right? Yeah. No, that's fine. That's fine. Yes. So what I want to do now is that I want to now do the double copy, and the claim that I can do it is because I have the same algebraic relations. So if something, as we will see, that this relation is actually something necessary, as we just heard, and if I now can relate them by just swapping them, I should try to do that and see if it's consistent. So let me do that. So often we just write that as, well, first of all, write m, and then we often write it as a square, which is a little bit of abuse of notation, because we're of course not squaring the denominator. So what I really mean is that we just square the numerator. Right. So the claim is that, first of all, this operation is valid, and it gives a gravitational amplitude. So let's try to unpack that. Okay. So the claim is that this is GR. But why? Why is it GR? Well, the claim is that you can always sort of bootstrap your amplitudes using 3 properties. So let me list those 3 properties, so specifically at tree level. So tree level, GR, amplitudes are uniquely fixed. Got the spell. Okay, so what are the, well, I'm going to pick 3 properties which I like. One of them is unitarity. And I'm going to combine this one with locality because they're kind of closely related in this context. And what this basically means are factorization properties at tree level. The second property is I'm going to impose that I have 2 derivative interactions. I really only need that to fix my 3-point amplitude. Because of course you know that at 3-point you can also write down higher derivative gravities, r cubed or whatever. So if I just impose 2 derivative, I will land uniquely on the GR 3-point amplitude. And then lastly, so unitarity locality only fixes the poles. You also need to fix your local terms. And the local terms are just fixed by diffeomorphism symmetry or gauge symmetry. Right. So if you have these 3 properties satisfied, then you can basically bootstrap your gravity amplitude to any multiplicity, writing down some ansatz and solving it. So I think we can probably convince ourselves that the first 2 properties are relatively straightforward. So locality here just means that I'm going to pick local numerators. I'm not going to have any other poles than the poles that are manifest. Unitarity basically means that when I go on the physical poles, they're going to factorize the lower point amplitudes. This was obvious in the construction. I just wrote it as a product of two 3-point vertex, so that's obvious. Also, since I used Yang-Mills is one derivative interaction, so I'm just squaring that, so I'm going to get two derivative interactions. Okay, so the most non-trivial property is diffeomorphism symmetry then. So let's check that this amplitude is actually diffeomorphism invariant. Maybe I do it here. So what I can do is that I can just do a gauge variation, or ward identity, or whatever you want to call it, on my amplitude. And essentially, it's just an operation where I replace one of the polarization with a momenta. So what I'm going to get, it's a bit messy, maybe. So I'm just going to define that delta acting on epsilon just gives, I'm going to pick one of the epsilon, so epsilon 4 of mu. That's just going to be P4 of mu. And then I apply it to the amplitude, and I'm going to get the factor 2 because everything is quadratic in epsilon. But then I'm going to get ns delta ns over s plus permutations, right? And you can probably convince yourself that the variation of the numerator has to be proportional to s, because how is it going to be gauging? I mean, how are you going to get some relation between the different terms otherwise? So it turns out that delta ns is equal to some function that I'm going to call alpha. So this is a function of s and t, I guess, u, whatever, and then it's proportional to s. You can work out what this function is. It turns out that this function is actually fully symmetric in legs 1, 2, 3, 4. It's just fully symmetric function. So this means that, in fact, let me erase this here. What you're going to get here is, in fact, you're going to get 2 times ns plus nt plus nu times this function alpha s of t. And by the way, if you do this in the Yang-Mills, you're going to get exactly the same thing, except you're going to get color factors here instead. So this actually is referring to the comment that yes, this is, the sum of these things has to be 0 for Yang-Mills if you have color factors, and it has to be 0 for gravity if you want to have diffeomorphic symmetry. So this has to be 0, meaning that this has to be 0.
You showed us in general, like for higher?
Yeah, I think that was also the comment. I think if you do it higher point, you don't get the unique 3-term identity, right? You get some more general relations between numerators, which also include some non-local denominators. There's some old paper by Pierre Van Hove, I think 15 years ago or something like that, where he worked out the higher point case of that. So yeah, so you don't get individual 3-term identities. So there is more freedom in the numerators. And it's obvious that there's more freedom, right? Because there's other ways to write. Yeah, there's other ways to write the amplitude than this color kinematic satisfying numerator. So there are other solutions that do not satisfy it, and then of course, while the double copy is different in that case, and it's more complicated. But yeah, let me not say too much more. Yeah.
Since already the 3-point amplitudes, sort of double copy structures are apparent, is
Yeah.
there the fact that I can recurse the 3 amplitudes in both theories down to 3-point amplitudes from outside recursion?
Yeah, that's a good question. You can wonder, can I use, let's say, BCFW, for example, to do it? But one feature that BCFW has is that it gives you very compact amplitudes, but they have spurious poles, right? And now you have to worry whether that's consistent, because you're going to square the spurious poles and are they going to cancel out and so on, right? And so if you use BCFW, you're sort of going in a perpendicular direction to this philosophy, right? You could try to do off-shell recursion, but that's just equivalent to Feynman rules, I guess. Yeah. So in general, the statement is that recursion doesn't work so well when you want to recycle some color kinematic satisfying objects. Also, if you try to recycle some loop expression going to higher loops, you have the same problem that things change in some chaotic way when you change the multiplicity or when you change the loop order. Okay, good. Okay, so some people have asked me already what happens at higher multiplicity. So let me just briefly do that then. So basically, we're just going to take the lessons of 4-point and just straightforwardly generalize them. And that will involve, maybe constraining things more than naively needed, but it just follows whatever is happening at 4-point, right? So the double copy at m points. So I call it m because I already used my n for something else. Also, m stands for multiplicity. So I have my m point Yang-Mills. This is color dressed. So it's just some sum over cubic diagrams. So let me introduce an index I, which runs over cubic diagrams. And then for each cubic diagram, you have a color factor, which is just a trivial one that you would get from sewing together FABCs. You have a trivial denominator factor, which is what you would get if you had scalar phi cube theory. And then you have a non-trivial numerator factor, which you cannot compute in some simple way from Feynman rules. You just have to solve for it. You can also, how many diagrams are there at tree level? That's 2m minus 5 double factorial. Sometimes you might have seen people counting diagrams in Yang-Mills, and it's very complicated, but it turns out when you turn them into cubic diagrams only, it's very simple to count them. Okay, good. And then, then you just impose the color kinematics duality, which is just the same as before, but now you have to do it many more times because you have to look at each subdiagram. So you basically have your S channel as before, but now this is a subdiagram into some larger diagram. So this is some blob. And permutations. So basically this is my S, and then you do the T and the U permutation. And the sum of those three diagrams has to be 0. And now I'm abusing notation again. What I mean here is that the color factor has to be 0 by Jacobi identity, and the numerator has to be 0. So specifically, CS, CT plus CT plus CU is equal to 0. Now, of course, ST and U are no longer referring to 4-point kinematics. It's just referring to this effective subdiagram. And likewise for the numerators. Maybe I just write I, maybe I I, J, K, just so it's clear that these are more complicated. I, J, K equal to 0. So whenever you see a three-term identity coming from the color algebra, you just write down the corresponding kinematic identity, and then you try to solve it. This one, of course, you don't need to solve because it's just arithmetic, but for numerators you need to solve unless you have a better way of computing them. All right, and then if you have now made sure that for every color identity you have a numerator identity, now I can swap color for numerators, and I can then double up my numerators. So let me write that here. Sum over I. Well, let me just say, well, in this case, I guess it is. Well, let me remove that label. So this is some gauge theory. This is some gravity theory. I also put a tilde here on my numerator because I could, in principle, compute this numerator in a different way from the other one, so they could be different. They could also have different states. I could have a fermion here, or whatever, a fermion here, and a scalar here, or whatever, right? So it doesn't have to be the same. They could also come from different theories. So that's why I have put a twiddle on one of my numerator. But both of them have to satisfy this identity, or, well, the correct statement is that at least one of this, either n or n tilde, has to satisfy this type of identity. And the other one need not satisfy it. But there has to be a way of rewriting the one that does not satisfy it such that you get to something that satisfies color kinematics duality in principle. Otherwise, you're going to have problems with gauge invariance. Okay, good. Yep.
So 1, 2, 3, 4 are internal lines here.
Yes.
Why the sum minus 0, not the sum of the PPI squared?
Yeah. Good. Yeah. So we're taking something that started off being on shell at 4 point, and now we're generalizing it. And of course, it's going to be off shell here. So it's no longer true that if I define some internal STU minus some invariance, yeah, the sum of them are not going to be 0. But we're still imposing that the corresponding numerators are, because we know that the color factors are, right? So the fact that at 4 point you have a sum over 3 color factors, 3 numerators, and 3 Mandelstams, it's a bit of an accident, I think. So, forget about the fact that the sum of 3 Mandelstams also looks like this type of identity, right? Yeah. So we're just taking some on-shell property. We're trying to generalize it for off-shell legs. These guys are off-shell. And so this is the natural way to do it. And yeah, thanks for reminding me. So another thing here that you need to make sure is that you have lots of sub-diagrams, right? You have, for example, at 5 point, I believe you have 10 different Jacobi relations. It turns out that not all of the Jacobi relations are independent. It turns out that only 9 of them are independent. But nevertheless, you get a lot of Jacobis, so they grow very quickly. And that means that the equation system that you get are quite complicated. Okay, good. Any other questions about endpoints? Okay, good. Then I have some remarks. This is probably going to take the rest of the time. So the first remark here is that the local numerators are gauge dependent. And furthermore, well, it's kind of obvious, they're non-unique, not unique. Well, you might know that in gauge theory and gravity, individual Feynman diagrams are not gauge invariant, so that's not a big surprise. What was a bit of a surprise was that, nevertheless, the 4-point numerators were more or less unique. But when you go to 5-point and higher, they're not going to be unique. Even if you impose all the natural diagram symmetries, it's not going to be unique at 5-point. So there's freedom, and this means that solving this system is hard because you have 3 parameters in the end of the day, and you don't know what to do with them. So it's non-trivial. Non-trivial to find so let me say non-trivial to find a gauge, let me put it in quotation mark, where ns plus nc plus n u is equal to 0. And here I really mean the internal subdiagrams. Here I'm really abusing the word gauge, because what do I really mean? Well, you could imagine doing some gauge fixing at the Lagrangian level of Yang-Mills and doing things, but that would clearly not be enough. You probably have to do some field redefinition, you have to introduce auxiliary fields. So all of that could go into the quotation mark gauge here in order to satisfy these identities. But furthermore, even if you don't derive this from some kind of Lagrangian, you can just imagine butchering your Feynman diagrams in various ways, such that these identities still are satisfied, but you made a mess. Anyhow, so it's complicated to find these numerators. However, they are known at free level for Yang-Mills. So closed form numerators known for Yang-Mills at free level. And I think the best way they were computed, or maybe the first time they were computed in a closed form was actually using some string theory inspired method, which is called the CHY formalism, and which is completely different setup. You start from a Riemann sphere, you solve some scattering equations, you get something very ugly, but then you massage it a bit, and people manage to figure out what the numerators are from that way of computing it.
So this is not closed form?
It's closed form in the sense that there is a prescription.
Right.
But
you can write the algorithm on a piece of paper.
There's an algorithm, okay. I think it's very close to a closed form.
To evaluate it at, say, 12 points, it's still going to take your laptop.
I think 12 points is doable, yeah. Yeah. Anyhow, there is a Mathematica program that computes them, and it doesn't do it by solving things. It just it just follows the recipe and it gives it right there.
But eventually it will lose over BCFW.
Lose
over BCFW. Because one is a recursion relation, the other one grows factorially, and eventually power is
yeah.
less bad.
Well, for computing numerators, it's completely doable. I think even to 15 point, but the problem is that then you have to feed it into the double copy sum over all the terms, and the number of terms is just humongous. But the individual numerators are not that bad, yeah. So in that sense, I mean, okay, maybe closed form is a bit overselling it, but. Yeah, it's not I don't think it's a recursion. It's just a formula, but the formula is very convoluted. Yeah, for the closed form, right? That short? Oh, BCFW. So BCFW, Peter Keshasu Feng Witten, is an on-shell recursion formula, And it's not used for computing numerators, but it's used for computing gravitational amplitude. So if you're just wondering what's the most efficient way of computing gravitational amplitudes, BCFW might be it. It kind of depends on which helicities you're looking at, maybe, because it's known actually that even for Young-Mills, BCFW kind of lose out to off-shell recursion if you just have complicated helicity configuration. But if it's simple enough, if you have like MHV next to MHV and so on, then BCFW is clearly the best way to do it. Anyhow, so I'm mentioning this because sometimes people ask, is color kinematics duality proven? And of course, when you ask a question, you have to specify which theory. So of course, the question refers to Young-Mills. And the answer is, it's more or less proven, at least to physics rigor, because there's an explicit solution for the answer, right? Now, this formula, I don't know if the formula was proven to always be true, but you know, they checked it up to very large multiplicity. Yeah, probably, yeah. But anyhow, so that's the origin. When people say it's proven, well, its solution is known. So okay, good. What's the next thing I was going to say? Okay. Yes, I did mention that, you know, the reason why numerators satisfy Jacobi relation is that has something to do with kinematic algebra, right? So the statement here that even though we know the numerators, we don't know how to generate them from anything like a kinematic algebra, right? So the kinematic algebra is not known for general cases of Young-Mills amplitudes. It is known in some particular examples, such as self-dual Young-Mills, which is not Young-Mills. It's just a very simple truncation of Young-Mills. And I should also say that, in principle, you can imagine that you had a Lagrangian way of computing numerators. That's also not known. So basically, Feynman rules for n not known. And the reason why I mentioned that is because these two statements are, of course, the same statement. If you have kinematic algebra, you have the Feynman rules, and vice versa. Which is obvious for color factors, right? The color factors, the Feynman rules for the color factors are just the Lie algebra, right? So that's, I think it's an important problem, but unfortunately it's a very difficult problem because people have worked on it and not managed to find a solution to it. Okay. The next remark is that you can generate, I mean, so far I only talked about tree level. I mentioned loop level a little bit. And loop level is basically automatic in the sense that the rules of the game is the same as loop level. So double copy and color kinematics duality. Let me write double copy and color kinematics duality generalize. And I have to be careful here. I mean the rule of the game generalize. So nothing dramatic happens. But the problem is that we don't know the numerators then. So numerators not known in general. Also, there's no proof. No proof of color kinematics duality. Let me say that if you can prove color kinematics duality, then double copy just follows automatically. So I don't think we need to prove double copy separately. This is what we need to prove. But there are many examples where it works. So it's confirmed to work. So the most impressive case is 4 loops, up to 4 loops. So up to 4 loops. N equals 4 super Yang-Mills. And so this is just a maximally supersymmetric version of the Yang-Mills. And in fact, the numerators are actually written on a d-dimensional form, so it automatically lifts all the way up to 10d if you want. So n equals 1 in 10d also works. Then, of course, the next question, what about just pure Yang-Mills? And here I would say that 1 loop, we're pretty confident. For example, there's 4-point 1 loop, 5-point 1 loop. So that works. So it's pure Yang-Mills. Even you could also say with matter as well. And the reason why I don't write 2 here is because people have seen some problems for the 2-loop amplitude. Likewise, people have seen some problems for the 5-loop amplitude in super Yang-Mills. And by that, I don't mean that people have proven that you cannot do it. It's just people have tried and it didn't get it to work. And yes, indeed. So these calculations here are very important for figuring out the behavior of n equals 8 supergravity. Because this is what n equals 4 super Yang-Mills double copies to. And using these calculations, we could actually compute the UV behavior up to 4 loops. And it's finite. In 4D. It's actually even finite a little bit higher than 4D. Not 5D, but slightly below 5D. And of course, the question is, does this continue to all loops? We are pretty confident. I would say there's even proofs that at 5 loop there's actually a calculation where it's also is finite, but even at 6 loop is known to be finite. 7 loops is not known, so that's the big question. Is n equals 8 supergravity finite at 7 loops or not? Because if it is, then that's a miracle, and if there's one miracle, maybe there's more miracles. But in order to know that, you have to calculate. I think there's no other way of knowing whether there's a divergence or not, except for calculating. And you need a framework which is powerful. This is a framework that's powerful, but we have issues at 5 loops, so that's a problem. I would say that if you just try to write down an ansatz and solve the numerators of 5 loop, you cannot write down the most general ansatz because it's just ansatz space is just too large. So you can't be very confident in saying that there is no solution. At 2 loop pure Yang-Mills, I haven't actually done the calculation. This was done by other people, so I don't actually know if they're limited in the ansatz space. But even so, you can write down. You can relax the framework in various ways. You can write down non-local numerators. You can do various crazy things. You can introduce more diagrams than you naively think you have because you can break symmetries between diagrams and so on. So there's a lot of things you can do, and such that it's very hard to prove that it doesn't work, even though you haven't found a solution yet. Okay, any questions on that? Okay. So for Yang-Mills and generalization of Yang-Mills, it looks hard, but you can always go to simpler case theories. So there are simple theories where everything works perfectly. So let me just mention that before we end, I guess. So a theory where everything works is Chern-Simons theory. And this is, of course, in 3 dimensions. Okay, so what works? Well, we have a proof of color kinematics duality to all loops. You might wonder, how did we do that? How did we do it to all loops? Well, in fact, we just wrote down, well, we just checked that the kinematic algebra is there, and it's there. So the kinematic Lie algebra is known. Well, it's just check what it is, and it is volume-preserving diffeomorphisms. So the generators for diffeomorphism is just vector fields. So pick any vector field, that's the generator for diffeomorphisms. And volume preserving are just the ones just the one that satisfies Lorentz gauge. Yeah, so pick a vector field satisfying Lorentz gauge, you get volume preserving diffeomorphisms. So in fact, all you have to do, you have to just pull out the Chern-Simons Lagrangian, put it in Lorentz gauge, and you're done. And because of how the propagator looks like in Chern-Simons theory, it's always going to impose Lorentz gauge automatically, even for internal fields. Okay, a bad thing about Chern-Simons theory, there's no amplitudes. This is topological. So you might say, well, what am I even talking about? Because I introduced color kinematics duality for amplitudes. Well, if it work off-shell, you can just check off-shell correlators in Lorentz gauge. They satisfy color kinematics duality. The off-shell correlators are non-zero, so you have very non-trivial numerators, and they satisfy all the needed relations. I should also say, of course, there's also Faddeev-Popov ghost in Chern-Simons theory. You can check that it works for them as well. So all the fields, the normal fields and the ghost field, they all satisfy color kinematics duality. I think this example also gives us a hint of what could be the kinematic algebra for Yang-Mills, because 10 years ago there was a paper about self-dual Yang-Mills where they also found volume-preserving diffeomorphisms, well, area-preserving diffeomorphisms, because they were looking at self-dual Yang-Mills, which is basically described by 2 variables rather than 3 variables. So we know that there's a subsector of Yang-Mills which has volume-preserving or area-preserving diffeomorphisms. So it's probably also true that the full theory has volume-preserving diffeomorphisms as a sub-algebra, and then there's some larger version of that. I don't know what the larger version is, but this gives us some clue. Oh yeah, so then you might ask, what's the gravity? Well, it's a bit tricky to answer this because, again, we don't have any amplitudes, right? You just get something that looks like a gravitational amplitude, but when you plug in your physical momenta and polarization, you get nothing. You get 0. There was a paper by Olaf Holm and company from Humboldt. They were saying that they were claiming that it's Codera-Spencer theory. And of course, I don't know anything about it, so I'm just repeating what they said. I should say, though, that yes, yes. Yeah, it's a good question if there's a relation there. I thought about it, but not enough to actually answer the question. One thing I should say, though, is that after this paper that came out that pointed out that it has something to do with Codera-Spencer, I look in the literature, And then I could conclude that this was actually well known for string theory, because this is just some topological string theory, and if you write down the string field theory Lagrangian, it exactly gives Chern-Simons theory, and there was some paper, I think it was by Vatha, and he says that there's also a closed string sector, of course, and yeah, so this is, the job copy is just the closed string sector of this. So in hindsight, it was known, but in a different language. But still, it's a very good example because it clarifies what the kinematic algebra should be in a consistent theory, which Chern-Simons theories. Okay, good. I think we're maybe running out of time. Yeah, so maybe I should end here. If there's maybe any questions, I can take them as well.
Certainly, thank Henrik, and maybe a quick question.
Yep.
When you say the alpha, what specifically are the elements of the alpha?
Yeah. I think if you ask some people who work on this, they don't want to commit to Lie algebra. I think Chris White is very convinced it's not a Lie algebra, so that's why sometimes I say kinematic Lie algebra, sometimes I say Lie algebra, or sorry, kinematic algebra. But here, in this case, this is clearly a Lie algebra. It's just an infinite dimensional Lie algebra. So you ask about the generators. So the generators, or the elements of the algebra, is just any function, any field, any vector field that is divergence-less, so Lorentz gauge. Now, maybe that doesn't answer your question, because you might ask, well, what's the another way to think of it is it's just all plane waves. Basically, just take your vector field, Fourier transform it, and now it's just a sum of plane wave with arbitrary factors. So there's just infinitely many of them, and they're plane waves. Yeah. I mean, I can even write down an example. Say again? What?
The reason for the kinematic Lie algebra is it's meant to realize relations between the numerators in your diagram.
Yeah.
So how will you be the elements of the algebra at that point?
Yeah, so here's a generator. So it carries a Lorentz index and its momenta if I go to the plane wave basis. So it's just a plane wave. And there's a derivative. And that's not enough. You need also a projector. So the projector, let me call it mu. So there's an epsilon mu rho nu p rho. That's the generator. And so because of this acts as a projector now, so it's always going to stay in Lorentz gauge. And this derivative just acts on this, so that's why they no longer commutes, right? So you get the non-trivial commutation relation. So.
All right, maybe now's a good time to break lunch. Let's thank Henrik one more time.